There are many types of energy that we are familiar with as they relate to things like power generation, such as chemical, nuclear energy, solar, wind, hydro, thermal energy, and the list goes on. Many of these can be grouped together into more fundamental categories. The fundamental types of energy that we will deal with in this course are kinetic energy, which is the energy associated with the motion of an object, and potential energy, which is the energy that is stored in some way. We will define various types of kinetic and potential energy and express equations for them as we go forward. Before we do that, here are some facts that are common to all types of energy. The first fact, energy is a scalar quantity, not a vector. A scalar doesn't include direction, however, it may be signed, such as temperature, which is a scalar. It can be positive or negative. The fact that energy is a scalar often makes our calculations simpler because we don't have to do vector math. On the other hand, we lose the ability to determine direction when doing calculations with energy, such as the direction that an object is moving, so it's a bit of a trade-off. The next fact is that the SI unit for all energy quantities is a joule. A joule is equivalent to a Newton times a meter or kilogram meter squared divided by second squared. Some other common energy units are a calorie and a food calorie. Usually when we use calories, we mean a small calorie, which is equal to 4.184 joules, while a food or large calorie is equal to 1,000 times that, or 4,184 joules. Electric energy is typically measured in kilowatt hours, where 1 kilowatt hour is equal to 3.6 times 10 to the 6 joules. The energy unit electron volts is commonly used for very small energies, such as those associated with atomic energy levels. 1 eV is equal to 1.6 times 10 to the minus 19 joules. And then BTUs and ergs are two other units that you may come across. And then one more fact is that all types of energy can be added together in an equation. Mathematically, that means we can add, for instance, kinetic energy to potential energy, etc. The last fact about energy is a fundamental principle in physics and one that we can often take advantage of when solving problems. This principle is referred to as the conservation of energy. The conservation of energy is stated in different ways. Here's one way to state it. Energy in total cannot be created or destroyed, but it can be converted from one type to another. One implication of this is that there is a constant amount of energy in the universe or in a closed system. What we mean by the term closed system is a system of objects that does not interact with objects outside the system. So that means that energy cannot be transferred into or out of a closed system. When energy is transferred into or out of a system because a force is applied to it, in physics we refer to that transfer of energy as work. So now let me define the term work in detail. The basic definition is that work is a transfer of energy to or from a system by a force that is acting on the system. Notice that, as indicated in the definition, a force is always involved when work is done to a system, or in other words, energy can only be transferred to or from a system because a force acts on the system. Based on this, we have a signing convention for work. If a force transfers energy into a system, then the work done by that force is a positive value, and conversely, if a force transfers energy out of a system, then the work done by that force is a negative value. Ultimately, we will have several equations that we can use to calculate work. Each equation has a restriction on it, so the one that is appropriate to use depends on the circumstances. The equation that I will give you now is perhaps the most common one used. The work done by a constant force on a system is Fx times delta x. And there in that statement is the restriction on this equation. We can only use this equation when the force is constant. Defining the variables in this equation, delta x is the displacement of the system, Fx is the x component of the force, or in other words, Fx is the component of the force that is parallel to the displacement. The F subscript on the W for work is a reminder that all work is associated with a force. So we might want to find the work by the gravitational force, or the work by the normal force, or the work by friction, etc. We might also want to find the net work done to an object or system, which is the total of all of the individual work values. We just add them together, keeping in mind that some are positive and some are negative. Here's a basic example to demonstrate the use of this equation. An object moves 5 meters to the right, and as it moves, a constant 2 Newton force is applied to it in the direction shown. Let's find the work done to the object by this force as the object moves 5 meters to the right. The first thing we can recognize is that the force is constant, and that means we can use this equation to calculate the work. To apply the equation, the first thing we should do is to define the coordinate scheme such that the x-axis is parallel to the displacement like this. When we do that, then delta x in this example is positive 5 meters. Also, based on this coordinate scheme, the x component of the force is here, which we can see is F times cosine theta. And plugging those numbers in, that comes out to be positive 1.6 newtons. We can then plug these values into the equation for work, and we find that the work done by this force to the object is a positive 8 joules. Because the work came out to be a positive value, we know that this force added 8 joules to the energy of the object. There's also another popular way to write this work equation. In this example, we found that Fx is F times cosine theta. This result is true in general, so in the equation we can replace Fx with F times cosine theta, and then the work equation can be written this way, where the cosine is typically just moved to the end of the equation. And so we can add this information to the summary of the equation. Finally, I'll summarize some of the concepts about work that are expressed by this equation. First, that the SI unit for work is a joule. Second, that work done is always associated with a force. Third, that a force can only do work to a system if the system moves. This might sound strange, but keep in mind that the physics definition of work is a transfer of energy, and energy can only be transferred to a system if the system moves. The fourth fact is that only the component of the force that is in the direction of the displacement does any work. Again, this is not necessarily intuitive, but consider a toy car that is rolling across a table. If you push the car in the direction that it is already rolling, then it will speed up, and so you did positive work to the car. But if you push straight down on the car, perpendicular to the table, then the car speed won't change, so you haven't done any work to the car. So hopefully that helps you to appreciate why this statement is true. The last fact is a technique for determining if the work done is positive or negative. We already know that work is positive if the force adds energy and it's negative if it removes energy, but in some scenarios it's not always clear if energy is being added or removed. So based on the equation, here's another technique. If Fx and the displacement are in the same direction, then that force does positive work. Conversely, if they are in opposite directions, then that force does negative work. In the example we just did, Fx and the displacement are in the same direction, so the work was positive. And so that brings us to the end of this video introducing energy and work. We'll continue to investigate energy further in the next few videos.